Okay, in this video we are looking at hyperbolic functions, which is the first part of chapter 6 from Core Pure Year 2. I split it into two parts, the second part of chapter 6 being about calculus with hyperbolic functions. This one's going to be about identities and equations and introducing these functions. And I always say in these videos, it is not possible for these chapter summaries to cover all of the possible ways that examiners can assess the topic. So it's very, very important that you are looking at exam questions and doing additional revision. This is here really just to kind of summarize what is contained in the playlist. So you should probably know these things off by heart, that the cosine or cosh, however you want to say it, cosh of x is a half of e to the x plus e to the minus x. Sine x is a half of e to the x minus e to the minus x. So the same thing, but with plus and with minus. Seems to kind of be like that in lots of identities. I wonder if you can think of any other ones where cosh or something to do with cosine is with plus and something to do with sine is minus. And then people say this in a different way. I say than, some people say tanch. I'll be saying than x in this one. It is literally just the sine x divided by the cosh x. So these halves the halves that we have here are cancelling out. And then lots of people go from this form to this form by simply multiplying everything in the numerator by e to the x and everything in the denominator by e to the x, coming up with this expression that we've got here. And this one tends to be a little bit more useful, but to be honest, I just memorize these and I can quickly derive this one if I need it. Now, in terms of what the graphs look like, the cosh graph or the cosine graph, the hyperbolic cosine graph, I'm going to say it properly, is this blue one that we've got here. It kind of looks like a bit like a quadratic. It is not a quadratic. It is something quite different. And this point that it is at here is 1, and that occurs at the x value being 0. Okay, it's completely symmetrical about the y-axis that we've got here. The sine graph is this red one. It kind of looks like a cubic graph. Of course, it's not a cubic graph, but it's roughly that kind of shape that we're looking for. And then the than graph that we have is sort of like a kind of rotated, sort of flipped around cubic graph. But the strange thing is that it is just between -1 and 1. It has these asymptotes. It never actually becomes 1 or -1, but it just kind of tends towards those values that we've got there. So what I want to do for the first part is actually to kind of prove an identity that we've got here, which is really just using these exponential forms and getting used to kind of practicing using lots of stuff to do with these e functions, these exponential functions we've got here. So it says, using the definition of cosh x in terms of exponentials, prove that cosh of 3a is equal to 4 cosh cubed a minus 3 cosh a. So this thing that we're aiming for, the cosh of 3a, we're hoping that we can make the right-hand side look like this. So it's going to be a half of e to the 3a plus e to the minus 3a. That's the thing that we're aiming for. And the thing that we're going to work on is our 4 cosh cubed a minus 3 cosh a. This should feel like the trigonometry stuff that we do in normal maths. If you don't use the identity symbol here, it is perfectly fine. You will not be penalised for that as far as I am aware. So we're going to be doing 4 multiplied by cosh a all cubed. By the way, I should mention I've started with this side that I want to work on because it's the messier side. There's more stuff to do with it. It's going to be a lot harder to kind of manipulate this. So cosh a all cubed, well, the half cubed is going to become the 8th, and then we're going to have our e to the a plus e to the minus a all cubed, and then we're going to have minus 3 times by a half, so that's minus 3 over 2, e to the a plus e to the minus a. And we're just going to keep manipulating everything on the right-hand side until it eventually looks like this thing that we've got here. So the 4 and the 8th gives the half that we have. And then I'm just going to be doing some binomial expansion on this to the power of 3. Pretty easy, because we know the coefficients are simply going to be 1, 3, 3, and 1. So there will be the e to the a all cubed, or e to the 3a. Then there will be 3 e to the 2a, and then an e to the minus a. There will be a 3 e to the a and an e to the minus 2a, and then there will be an e to the minus 3a for this part. And then I guess I can expand these brackets. We're going to have a minus 3 over 2 e to the a minus 3 over 2 e to the minus a. And you can kind of see how we're working towards this thing that we want. We only want it to be left with the 3a's and the minus 3a's in the powers. So I'm hoping that these things are going to cancel out with something in a moment. So let's just quickly do a little bit more work over here. I'm going to do quite a bit of expanding. So I have my half e to the 3a. I will then have plus 3 over 2. This is going to simplify. 2a and minus a is just going to be e to the a. We will then have 3 over 2 e to the minus a. And then we have a half e to the minus 3a. We then have the minus 3 over 2 e to the a. And the minus 3 over 2 e to the minus a. I think it's hard really just to keep track of where everything is. So this one does cancel with this one cancels with this, meaning we are left with a half of e to the 3a plus e to the minus 3a, which we said at the very beginning was our definition of cosh 3a. So we have proven that this thing that we have here is equivalent to cosh 3a. Now what's likely in a question is they then might ask you to use this in some kind of way. They might use this as some kind of identity that you can then use to solve an equation. But I'm now going to introduce the idea of how we can go about solving some equations down here by introducing the idea of inverses. Now, because the cosh, the sine, the than functions are all written in terms of exponentials, it makes sense that their inverses are in terms of logarithms. By the way, I will be introducing the idea of their reciprocal functions, sech, cosech, and coth, which are similar to sec, cosec, and cot. I think I'll be talking about those a little bit in the next video when we start doing some things to do with differentiation and integration. Anyway, these are given in the formula booklet, okay? So we have this one for r cosh, which we know is sometimes written as cosh to the minus 1, r sine, and then we have this r than one that we have here like this. Now, I wanted to quickly talk about something. When they give this to you in the formula booklet, the r cosh part, it only has one branch like this. The reason it only has one branch is because it wants it to kind of be like a function, okay? It's a bit like when you have like a y equals x squared, and when you do the reciprocal of it, not the reciprocal, but the inverse, you have like y equals square root x rather than the plus or minus square root x. So what I'm really saying here is, if you were to solve an equation for a cosine graph, or a cosh graph, you will see that there are two solutions, but the way it's given to you in the formula booklet is just this positive part of the branch being reflected over the line y equals x. And the reason that is because of wanting to keep it as a function, you know, the whole stuff to do with many to one and one to many, all of that kind of stuff that we've got here. So if you do want to solve an equation that is using r cosh, we can just adapt this formula a little bit so that we can either write it as plus or minus ln of x plus the square root of x minus 1, corresponding to the fact that you have a solution over here, and you also have the negative root that's just on the left-hand side as well. Or the other way that you can write it is just your ln of x plus or minus the square root of x squared minus 1. So the formula book kind of gives it to you in just one way. You can have the plus or minus outside the front, referring to the two solutions, or you can have the plus or minus inside, also referring to the two solutions that you have. And remarkably, this is an equivalent form to this one that we've got here. We're going to start off by proving that sine inverse of x is this thing that we've got here, in other words, this one. And I deliberately wrote it in this form to remind you, you can have r sine, which is the equivalent to sine inverse like this. So I'm going to begin by saying, well, let's let the inverse sine of x be equal to y. And so my aim in this case is I'm trying to find out what y is equal to. So rewriting this, I get that x is equal to sine y. Makes sense, right? If this is the inverse, apply it to both sides, that cancels, and you get left with a sine y. So let's use the definition. That is going to be a half e to the y minus e to the minus y. That's the definition of sine y. And my goal is to find out what y is equal to. So I'm going to double both sides so that I get like this. And then this is the part that you're going to find yourself doing quite a lot in these questions. We're going to try and create a pseudo-quadratic, meaning a quadratic in terms of e to the y. And I'm going to do that by multiplying everything by e to the y. This will give me 2x e to the y equals e to the 2y minus 1. Obviously, this times this just gives you 1 because you have something to the power of 0. Now, if I put this all on one side, I get e to the 2y minus 2x e to the y minus 1. Now, this looks like a quadratic equation that we've got here. We've got kind of the squared term, the sort of the non-squared term, and then the constant that we have at the end. You could use the quadratic formula if you want to. You can do whatever technique to do this. I'm going to do it using completing the square because I'm pretty old school with that, and I always think of completing the square as like a very traditional way of doing this. And it looks like it's screaming out completing the square because of this doubled coefficient here. I'll tell you what I might also do. I might make it really clear that it's a pseudo-quadratic by doing this. I might say, let's let u equal e to the y, so that we have u squared minus 2xu minus 1, okay? I'm going to jump up here so that I have enough space to finish this off. So if I complete the square, again, you don't have to complete the square. If you want to, you could just use the quadratic formula. We would get u minus x all squared we minus the x squared, and we still have the minus 1 that is there from before. So I'll have the x squared and the plus 1 on the right hand side, which will give me the u minus x all squared, and I'll square root it as well. Now I'll explain in a moment why we don't have the plus or minus square root for the shine one. Partly it's to do with just the shape of the graph, that when you think about reflecting that over the line y equals x, you're always just going to have one solution, but I will explain in just a second why we only have that one solution. So u is equal to x plus the square root of x squared plus 1, but we did a substitution where we said that u was equal to e to the y. So e to the y is x plus the square root of x squared plus 1. Finishing off, y, which we have said is the inverse shine of x, is equal to the ln of x plus the square root of x squared plus 1. So let me just explain why we didn't do the plus minus here. If this was a minus in front, okay, if there was a minus here, there would be a minus here. We would have the ln of x minus the square root of x squared plus 1. The square root of x squared plus 1, well, x squared plus 1 is a bit bigger than x squared, which meaning its square root is going to be a bit bigger than x. If we do x subtract something a bit bigger than x, we get something that's negative. We cannot take a logarithm of a negative number that we've got there. So that's why we only took the positive square root in this one. And actually that's why for this one we are allowed the plus and minus, because there's no restriction on this part necessarily becoming negative inside that bracket. So I'm going to use this idea of these inverses up here to solve some very simple equations, and then the next part we will do some more complicated ones here. So the first equation is that shine x is equal to 3. So this is just that x is equal to r shine, or the inverse shine, of 3. Using the formula, I've got it written literally just up here. That is just going to be the ln of 3 plus, oh my gosh, why can't I select that properly? The ln of 3 plus the square root of 3 squared plus 1. In other words, the ln of 3 plus the square root of 10. This one, do a quick bit of manipulation first. 4 divided by 2 is just 2. And so x is going to be the r cosh of 2. Now, this is where you're going to do the plus minus with the formula. You can either use this version or this version. You can try the other one, whichever one I don't do. You can try it and you will see that they are exactly the same numbers. I'm probably going to do the plus or minus just outside the front. So it's going to be plus or minus the ln of x. It is x plus the square root of x squared minus 1. So x plus the square root of x squared minus 1. So x is plus or minus the ln of 2 plus root 3. The alternative, like I said, is 2 plus or minus root 3 like this. It is exactly the same thing. Just give your answer in one of those forms that we've got. And then again, think about what this one might be. I have shine and cosh. Let's create than so that I can use the inverse than that we've got as this bottom one here. So I'll divide by cosh so that we have 4 equals 5 than x, meaning that than x, which feels very strange to say, is equal to 4 over 5. And so x is, looking at the formula, I'm always using the formula for these ones, it's the ln of 1 plus x over 1 minus x. So that's 1 plus 4/5 over 1 minus 4/5. Let's just do that on my calculator. That's 1 plus 4/5 over 1 minus 4/5. That's 9. So x is a half ln 9. You know what? I'm tempted to write that more neatly. We know that a half ln 9 is ln of 9 to the power of a half. In other words, x is equal to 3 for this part that we've got here. Okay, next up we look at solving equations using identities, but also using Osborn's rule as well, okay? So we have this kind of equation we're going to try and solve, and if you imagine it wasn't hyperbolic and it was just normal trigonometry, you pretty much know what you need to do. You need to use lots of different identities to try and get this into something we can solve, and we go from there. But we're going to make sure that our identities are slightly adapted, and we can use the adaptation of something called Osborn's rule that we've got here. So you can convert any trigonometric identity to a hyperbolic one by using Osborn's rule. All you do is you rewrite the identity you would typically use with hyperbolic functions instead of trigonometric ones, and you negate any terms where there is a product or an implied product of two sine terms. So for example, if in our normal identity we had a sine x, sine y, When we converted it into a hyperbolic one, we would have it as negative sine x, sine y. We've converted them to hyperbolics, and we've negated it. And then the one that's maybe a little bit harder to spot is that this is an implied product of two sine terms, because when you have tan squared, that is sine squared x over cos squared x. So secretly, there is a sine squared in the numerator, which means when we write it in its hyperbolic form, we also need to negate it, as well as writing it as tan squared x here. So the tip for these equations is approach solving them in the same way as a trigonometric equation. Look at the arguments, decide if you need to convert any sines to cosines or vice versa, and go from there, okay? So let me just quickly go back. For some reason it undid that. We're going to go about solving this equation. We're going to use some identities, and we'll also use Osborn's rule for this. So there's a couple of things we're going to need to work on. I think the most obvious one we're going to need to work on is this argument over here, which is 2x, okay? I know that for cosh, or even for cos 2x, I can come up with identities that will give me sine squared or cos squared, but I also have this sine x, or sort of sine x over here. So I think I'm going to select the identity for this part that is going to be the one in terms of sine x, okay? Now we know that normally that cos 2x is equal to 1 minus 2 sine squared x. So using Osborn's rule, cosh 2x will be 1 plus 2 sine squared x, okay? That is going to help us deal with this part that we've got. Then this will give me this in terms of sine squared, this will be in terms of sine. I need to get rid of this cosh squared, and I need to write that in terms of something that is sine squared. So normally we know that sine squared x plus cos squared x is equal to 1. So if I do the hyperbolic version of this, I will have minus sine squared x plus cosh squared x is equal to 1. In other words, cosh squared x is equal to 1 plus sine squared x. You might have even thought to yourself, oh, well, cos squared is 1 minus sine squared, so cosh squared is therefore 1 plus sine squared. So I can put that there, and I can put that one there, and I think we should be able to solve this one nice and neatly. So I will get 1 plus sine squared x using Osborn's rule, and I don't need to state that, we can just use it straight away. And then on the right hand side, I have two lots of 1 plus 2 sine squared x. So I had to use two identities, both of them used Osborn's rule. One to deal with the 2x, and one to get everything in terms of sine, meaning I can then use it as like a pseudo-quadratic. So I have 1 plus sine squared x plus 4 sine x is equal to 2 plus 4 sine squared x. Looks like a quadratic to me. So I'm going to subtract the sine squared. So I have 3 sine squared x. I'll subtract the 4 sine x, and I'll do the 2 subtract the 1, which is a plus 1. I can either put this on the calculator. I actually think this looks like it should be pretty easy to factorize. I say that, and then I'll probably make a mistake. No, this looks easy. It's just going to be a minus 1 and a minus 1, because we therefore get the minus sine x, the minus 3 sine x to get this, and we get the plus 1 at the end. You could have done it on the calculator, though. That would have been fine. So this one is telling me that sine x, or 3 sine x, is equal to 1. So sine x is equal to a third. And so x is r sine 1/3. Again, using the formula, I think it is where you do ln of x. So it will be x plus the square root of x squared plus 1. I'm just going to double check that that's what it was. Yep, ln of x plus the square root of x squared plus 1. Let's actually tidy that up a bit. So a third squared plus 1 square rooted plus a third, that is this. So x is ln of 1 plus root 10 over 3. That's one of the solutions. And then for this one, we just have that sine x is equal to 1. So if sine x is equal to 1, this means that x is equal to r sine 1. In other words, x is the ln of 1 plus the square root of 1 squared plus 1. So x is equal to the ln of, what's that going to be? 1 plus 1, that's root 2. 1 plus root 2. Ln of 1 plus root 2 for this. Yep, I think that's the right answer I was looking for. Sometimes I'm checking just to make sure I've definitely not made any mistakes with this. What I would probably do if I was in an exam situation is I would plot this graph. If I had my graphics calculator, I would plot this graph and I would make sure that they intersected at these 2 points that we've got here. Okay? So the last thing I want to have a look at is solving equations where using exponential form is maybe a better approach that you have. And there's often a couple of clues that would help us with this. So I've said if a trig identity doesn't jump out to you, using an exponential form will work too. Now this one, I suppose, there's not really a trig identity I can use. And also there's an exponential term that's on the right hand side. So it kind of makes sense to take this away from hyperbolic functions, put it back into exponential form and just make it like a normal equation that we might solve. So left-hand side is going to be 2 times by cosh x. Well, that's 2 times by a half, so 2 over 2, e to the x plus e to the minus x is equal to 4 plus 9 e to the minus x. So we have e to the x plus e to the minus x. I'm then going to say that we have minus 9 e to the minus x minus 4 equals 0. In other words, we have e to the x minus 8 e to the minus x minus 4 equals 0. Now, again, I think we're going to create one of these kind of pseudo quadratics. So I'm going to multiply everything here by e to the x. So we get e to the 2x minus 8 minus 4 e to the x. So kind of writing it in the more standard form, that's e to the 2x minus 4 e to the x minus 8 equals 0. I am going to be a bit lazy here. I'm actually probably just going to put this one on my equation solver. So this is, my coefficients are 1, minus 4, and minus 8. And we get here that e to the x is equal to 2 plus 2 root 3, or e to the x is equal to 2 minus 2 root 3. However, this one has no solutions. And you'll see on your calculator, 2 minus 2 root 3 is negative 1.464, something like that. And e to the x is always greater than 1. So actually, sorry, e to the x is always greater than 0. And that's the reason that there are no solutions for this. So this part that we have is just that x is therefore the ln of 2 plus 2 root 3. And this is the only solution that we have to this equation. Again, in an exam context, I'd probably put this on a graph, and just see that they only cross in one location. So this one, we're going to solve this equation, giving our answer or answers in exact logarithmic form here. We have 2 sine x minus 3 cosh x plus 3 equals 0. Now, this is on a page where we're going to do it using exponential form. I want you to think, though, there is an alternative way to answer this question. Think about how you might do it in trigonometry, and can you think what that might be? And I will tell you after I've done this one in exponential form, okay? So 2 sine x, I'm going to be a bit quicker here. There's a half, right? So if I'm multiplying that by 2, there's just not going to be the half. So there'll be an e to the x plus, for sine, the definition is minus e to the minus x. I then have minus 3 times by cosh. That's minus 3 over 2 e to the x plus e to the minus x plus 3 equals 0. So I'm probably going to make life a bit easier by just doubling everything at this stage, and make sure you really do double everything. There's so many times like that where I say I'm going to double everything and I forget to double, I don't know, maybe this 3 at the end or something like that, and it kind of ruins the whole question. So just expanding these brackets out that we've got here. And then I'm going to collect some like terms together, and then I'm going to do that same trick of multiplying through by e to the x. So I have a 2 e to the x minus 3 e to the x, that's minus e to the x. I then have minus 5 e to the minus x plus 6 equals 0. I want it to look kind of like a normal quadratic, so I'm going to put some stuff onto the right-hand side. There'll be my e to the x, there'll be my plus 6, and there'll be my plus 5 e to the minus x. When I times everything by e to the x, I get e to the 2x plus 6 e to the x plus 5. So I can go straight in. I can factorize it, but it's pretty obvious what this is going to be. But I'm going to just use the equation solver for this. So my coefficients are 1, 6, and 5, meaning that e to the x, oh my gosh, I think I've done something wrong here. Yes, I have. When I put this to this side, the reason I did something wrong is because I got, for this equation, I had a negative 1 and a negative 5, meaning there was no solutions. I knew I'd planned for there to be at least one solution. When this 6 moved to the right-hand side, of course, it was supposed to become a negative 6, so that should be a negative 6 there. Apologies for that mistake. I hope you noticed it quicker than I did. Meaning that e to the x is either equal to 5 or e to the x is equal to 1. So this is just that x is equal to ln 5, x is equal to ln 1, which is obviously equal to 0. So our solutions are 0 or ln 5. Now, did you think of what the alternative way might be to answer this kind of question? I'm hoping you might have thought in normal trigonometry, if we had something like 2 sine x minus 3 cos x, you might know that you can write this in the form of r cos or r sine, which I think this one would be. I'd probably write this one as an r sine of x minus alpha. So probably what we could have done for this one is we could have written it as r sine of x minus alpha. I'm not sure if it would be better with sine or cos or plus or minus or something like that. But if you really wanted to, you could have answered this using a harmonic identity instead to combine these two things into one single term, and it was solvable from there. So I think they do a couple of questions like that in the textbook, so do watch out for those ones. So in the next video, I will be finishing off this chapter, which is really where we take these functions and we do some differentiation and some integration with them. And it kind of is a complement to some of the stuff from methods in calculus, which is why I like to really keep these two parts of chapter 6 separate. So I hope this was useful for you and that I will see you in another video sometime soon.